This is the last set of supplemental notes for this chapter. This is specifically on Freefall. So, this first information, right, we're talking about Freefall. If you look at it, this is all just background information as far as how did it come about and what did people used to think way back in, back in the day in the, right, 1500s and 1600s and in BC, so just a little history lesson there. But when we get to this part here, right, we see that on the Earth, gravity exists as a force on everything with mass, right? The force is a push or pull. The force makes all objects accelerate downwards towards the center of the Earth. This acceleration varies a little bit, but you can see it's kind of, looking at it, it's 9.83 and 9.78. Basically, it's 9.8. Well, the nice thing is that they're actually going to let us use 10 for the acceleration of gravity. It makes it just easier when you're doing multiple choice questions, and just dividing and multiplying by 10 obviously is a lot easier. So you don't need to bother to use 9.8, just use 10. The symbol in equations for gravity is a lowercase g. So you can substitute anytime you have acceleration. If you substitute in a lowercase g for an a, it's understood that that object is accelerating at the rate of gravity, so it's accelerating down at 10 meters per second squared. Okay. So looking at some example problems, right, remember that direction is the key here. So for us, we're going to make down a negative direction and up a positive direction. And if we all do it the same, then hopefully when we look at each other's work, it'll make sense. So we have a ball is thrown straight upward. If it takes 4.25 seconds to reach the top of its path, what is the initial speed? It says since the ball is traveling upward and the acceleration is downward, the ball will slow down as it moves up, and we all know that it'll slow down. For the upward part of its motion, its final velocity will be 0, right? When it reaches the very highest point, the very highest peak, it will have to stop moving so that it can then start to move down. So it will then momentarily come to rest and then change direction and begin to accelerate downward. Since we know that for the upward part of its journey, the final velocity is 0, we can easily calculate the initial velocity. So if you look at this equation, right, that v there on the side, remember that that's essentially the final velocity, or it's the velocity that it's moving while at that instant in time, right? So it's kind of the instantaneous velocity after the time has gone by, and in this case, right, it was 4.25 seconds have gone by. So using that equation, right, we know that the initial velocity, the final velocity was 0, so we got rid of that in the equation, and we ended up with rearranging it to look like that, plugging in the numbers, right? The acceleration is down, so it's a negative value. Time is a scalar quantity, so that's always a positive value. And so you end up with 42.5 meters per second. Now, if you look at these problems and you're not sure what you're looking at, realize that you look at the units. What do we measure in seconds? Well, it's time, right? And you'll always know that the acceleration is going to be that of gravity for objects that are in free fall. Okay, it says that, let's see here, right, just a side note, right, our velocity ends up being a positive value, meaning it's going up. That makes sense. It was thrown up, so it's going up. The acceleration was down, so it's negative. The time, again, is scalar, so it's always positive. Looking at number 2, a stone is thrown straight up from the top of a building with an initial speed of 35.5 meters per second. Right, it's thrown up, so that is going to be a positive 35.5. How high does it go from the top of the building? So let's see. Looking at, right, what we're given, we know that the initial speed is this 35.5. If we want to know how high it goes, well, what do we know about this final velocity? At the very highest point, right, it's not going to be moving. We're looking for how high, and of course we know the acceleration of gravity is 0. So again, right, velocity at the top is 0. So plugging in our values, we're putting it in a positive 35.5, a negative 10 for acceleration, right, getting you that the change in position was 63.01 meters high. So it changed position in a positive direction. It got higher and not lower. Part B, how much time to reach the maximum height? Well, if you're looking at the values, and sometimes it's sometimes it's a good idea to write down the givens as I've done in class because it helps you identify the equation. Well, in this case, right, our equation that we're using is this v equals vo plus at because we know the acceleration. We know the initial velocity is still that 35.5. We still know the final velocity at the top is 0, but now we're looking for the time, and time is included that in equation where it was not included in this equation that we use for part A. So punching in our numbers, right, we go that our final velocity is 0, the initial is 35.5, our acceleration is negative 10, right, so two different directions there, and we get a time of 3.55 seconds, right? That's one way. Here's another way. We have that other equation. Well, we actually have enough information to find that out because, right, we know that in that time, this is how far it went. So it went 63 meters, right, to the highest point. So our highest point, right, the change in position was 63. Our acceleration was negative 10. We know the initial velocity was our 35.5. Therefore, you can find the time it took to get to the top. So two ways of finding the same thing. Part C, how much time does it take to get back down to the top of the building? Well, the time to get up equals the time to get down. So if it took 3.55 seconds to get up, it takes 7.1 seconds to get down. Part D, if the building is 45.2 meters tall, how much time will it take to hit the ground from when it was initially launched? So realize that what we're saying here is that if this is the building and this is the ground, right, it is being thrown up and then it's coming all the way back down before it hits the ground. So that's a little different than what we were doing here, because this was, it was going up and then it was coming down and it was landing at the same height that it was thrown. Because now it's landing below where it started, right, we know that it's going to land below where it started. So now we know that the change in position, right, this is hard to write, is actually going to be negative, why is that not working? Negative 45.2 meters because it's landing below where it started. So let's take a look at the work here. Right, using that equation, when we start plugging in our numbers, notice, right, I said negative 45.2 meters because from here, the starting position, to the ending position, it is negative 45.2 meters. I don't care that it went up and then came down. I only care about starting to ending. I don't care about the path taken. So you've got to get used to using that in the equation. So that being said, right, we know our acceleration is negative 10. The initial velocity is still 35.5. So getting us to this portion for the time. Well, hopefully that rings a bell that you have to use the quadratic equation. You do not need to show this work here, but right? And when I say this work, you don't have to show this work. You actually didn't even have to show this work. You should plug in the numbers. You should show what it would look like before the quadratic, and then you can just punch that in your calculator and tell me what the answer is. So that's one option. Okay, the second option, let's see here, right, is if you go through, you could split it into parts and figure out what happens, right? You could say, okay, well, when it gets back down to the height that it started at, when it gets down to, let's see if I can get a different color, when it got back down to right here, we know it was gonna fall 45.2 meters, right? But up here at this very top point, we know that it was 63.01 meters. So it was going to fall a total distance of 45.2 plus 63.01. And the convenient part about that is, what was the initial velocity at this point? At the very highest point, it was not moving. So if we put that as our starting position, we will get an initial velocity of 0, and from that point to the ground, right, it's going to fall over 100 meters, and it's going to take just 4.65 seconds to just do this portion of the fall. Well, remember, we know it took 3.55 seconds to go from here up to the top. So now we've kind of put it in parts. We know it took 4.65 to fall, it took 3.55 to get to the top. Putting those together gets you the total time of 8.2 seconds. Okay, number 3. Do number 2A and B again, but don't use the numbers. Solve it in terms of VO, G, and YO. And it says do part B first. This is something typical that happens on the test. They have you on the AP test. They have you solve for variables instead of solving for values. They won't even give you any values. So remember, for part B, right, let's see, what did we want? We wanted to find out how much time does it take to reach the maximum height. So using that same equation, right, we want to be in terms of VO, G, and Y. Well, we know that the acceleration is G, right? So we substitute in G for A. We know that the final velocity was 0, so we can just get rid of that. So taking this equation that we had before we plugged in values, we're just rearranging it to solve for what time looks like, right? So time would be negative initial velocity divided by the acceleration of gravity. And you don't want to put in the negative 10, you just want to put in G instead. So for part 1, let's see where to go. It says, how high does it go from the top of the building? Oops. So now that we have this value for the time, we are going to need to use it over here. So using what we were doing before, remember that this here essentially was the change in position, right? Because the change in position would be the final position minus the initial position. And so we took this negative initial position and we moved it on the other side of the equation, which is why it's now a positive, right, initial position instead of negative as it was shown in the equation. Hopefully that makes sense. So this is where it gets crazy. Hopefully they won't make us do too much of this stuff, right? Substituting everywhere that it says time, right, where we have time right here and we have time right here, we have to put in this statement. Oops. We have to put in the statement of negative VOG. So you can hopefully see, right, that for the t squared, you put in this negative VOG, right, and it's squared, so it's negative VO squared over G squared. And for this time, right, we put in negative VOG, and then it's just algebra and trying to reduce it to the simplest terms. Right, the negative VO squared becomes positive VO. The G squared here with the G here, right, cancels out to just G. Now we have a common denominator, so you can add those together. So 1/2 of VO squared over G minus VO squared over G, right? It's understood that this is basically a 1, right? So negative 1 plus 1/2 gives us negative 1/2. So that ends up with this equation here, right? And just, I know that there's this 2g on the bottom. You could just have left it negative 1/2 times VO squared over G. And looking at it, wow, that's really sloppy handwriting. It is in terms that they were looking for. So, and these types of problems kind of freak people out. Just realize that you'll have some time to get used to this throughout the course of the year. So by May, this really won't be that big of a deal. Okay, last problem, number 4. A rocket moves straight upward starting from rest with an acceleration of 29.4 meters per second. So it's not in free fall during this time. It's accelerating up. It runs out of fuel at the end of 4 seconds and continues to coast upward, reaching a maximum height before falling back to Earth. So A, find the rocket's velocity and position at 4 seconds. Remember, this is a typical acceleration problem. It's not in free fall because the rockets are firing. So looking through our equations, this is the one that makes the most sense for us to use. We can go through. We know it started from rest. The acceleration was positive 29.4 because it was going up, and it was for 4 seconds. That gets us our velocity at 4 seconds. And then here we can find our change in position, right? We now know that the velocity after 4 seconds was 117.6. We know it started from rest. We know that it had a positive upward acceleration, and so we can figure out how high. So we now know at this point right here, right, it is going 117 meters per second, and the rocket is, oops, all the way to the ground. It is 235 meters off the ground, right? Obviously it's 235.4 and 117.6, but you get the idea. So part B wants to know the maximum height of the rocket. Well, at that purple dot, right, you run out of fuel. Now it's a free fall problem. So we now know that from here to here, the object is in free fall. And of course, at the maximum height, the velocity is going to be 0. So you know when it starts to be an object in free fall, it's going positive 117.6 meters per second. At the end, it's going 0. And during that path, because it's in free fall, the acceleration is negative 10 meters per second squared. So using that, right, like I said, the velocity when it becomes an object in free fall is 117.6. It's accelerating at gravity. You can use 9.8 if you want, right? and I did that on purpose. Sometimes people will use 9.8, sometimes they'll use 10, but it was going up, so this is a positive number. The acceleration is down, so it's negative, and that gives you a positive change. Well, that's not the maximum height though. That's just the height from here to here. Remember, it's already 235.4 meters off the ground, so the maximum height is going to be the combination of those two values. So the rocket gets a total of 9.41 meters off the ground. Part C says find the velocity the instant before the rocket crashes to the ground. Well, we know, remember, I'm going to erase some of this stuff. It's getting kind of messy. We know that at this very highest point, we know the height above the ground, and we also know that the velocity at this point is 0. So it's actually a pretty easy problem once you know that, to find out how fast it's going right before it hits the ground. So using that equation, right, we can say it's going to fall that 941 meters. It's falling, so it's negative. The acceleration is down, so it's negative 9.8. Right at the highest peak, we discussed that the velocity was 0, and therefore it's going to give us a velocity of 135.81. Now notice that I have this positive and negative in here, right? Because this is a squared value, that means that it could be negative 135, it could be positive 135. So you need to look at the problem and realize that at this point the rocket's going down, and we've designated down as a negative value, so you need to say it's negative 135.81, not positive 135.81. That's a very common mistake, and people end up losing points in that.